Hello, and today we're going to be talking about stress-strain relationships. You are probably familiar with the uniaxial, the normal type strain, where some rod is being pulled along a certain direction, that is, its axial direction, through its center, through its axis. And that pulls and stretches, and that operates with the general relationship of sigma equal to the Young's modulus times the strain. This is very basic. This is something that you should hopefully be very familiar with. But what if we are dealing with something in 3 dimensions, something with shear, where the force is pulling not axially, but upwards or downwards along the edges of the sample? How does shear affect this stress or strain, if it does at all? Well, it turns out that shear type torsions and shear forces also do affect the stress and strain of an object. As we can see, a strain along the x-axis is given as the stress along that x-axis over E. So this is that same general formula that we see for the 2D, but also that minus the Poisson's ratio times the sum of the 2 directions that aren't axial, so the 2 shear directions, these 2 shear forces. So we get a strain along this x direction that is being both affected by stresses in the x direction as well as the y and the z direction. Now this follows for the other 3 directions as well. As you can see, this kind of general formula for stress over E, that's summed up, minus the Poisson's ratio times the 2 other directions, the 2 directions that aren't acting axially. This seems kind of pretty intuitive. This is a general idea for when it acts axially and how it behaves for the other 2 directions. So we start from this, we get stresses and strains that are kind of more in vector notation. So we have some sigma ij, so in 2 directions, is given as E times the strain in that same direction, that ij, divided by 1 plus Poisson's ratio, plus Poisson's ratio times the Young's modulus times the strain in this kk direction. So if you are familiar with vectors, ij being corresponding to maybe an x and a y, and k corresponding to a z, followed that times this kind of delta ij, so in the same direction. All that divided by 1 plus the Poisson's ratio times 1 minus 2 times the Poisson's ratio. That's the general equation that we will be using for these stress-strain relations. Notice how it relates the same direction to different directions, to this vertical direction or this direction that's cross-secting these 2. Alright, so we continue with rearranging this then for the strain. The strain in this type of direction, this ij, this E epsilon ij, is given as 1 plus V over E times the stress in that same ij direction. This is then subtracted from V over E times the stress in this kk direction, so in this perpendicular direction. If this is the I and j, this is the k, so the x, y, and z, and then also again this delta ij. So these are the kind of basic relationships that we'll be working with for these 3D cases. Now we can analyze these using these kind of ij equations, these kind of vector type equations, or we can also analyze these using matrix or matrices. We will begin with this type vector notation, so let's work on an example then. Given the sigma ij, the Young's modulus, and the epsilon, the delta, and the other epsilon, we are going to try to find the Poisson's ratio, the shear's modulus, and this sigma kk, so the sigma acting perpendicularly or normally to the other two. So, with a sigma ij of 50 kilopascals and Young's modulus of 30 megapascals, epsilon ij of 1.05 times 10 to the negative fourth, and delta ij equal to 1.65 times 10 to the negative fourth, and ekk equal to 2.15 times 10 to the negative fourth. We will try to use these values to determine these three things up top. So, going back, we have our equation of sigma ij, or sigma ij is equal to this big value here, relating these epsilon ij terms to these sigma terms. We will use this to try and find the Poisson's ratio, because we have this sigma, we have this epsilon, we have these two Young's modulus, we have this epsilon and this delta. So we will try to plug them in and find V. So, plugging in the numbers and actually putting it into Wolfram alpha, we get a Poisson's ratio of 0.5. So, I mean, very simple. With all the given information, we are able to directly plug into the equation and determine this Poisson's ratio. So, what is the Poisson's ratio? Hopefully, for those of you who are familiar with it, it relates the Young's modulus to the shear modulus. So, given the equation that relates these two, we have the Young's modulus is equal to 2 times the shear modulus divided by 1 plus this Poisson's ratio. Once again, plugging in the known values of 30 megapascals and dividing then by 1.5 and multiplying by 2. Sorry, this is backwards actually. We get a value of 22.5. So actually I will correct this. This should be a 2 and this is a 1.5. But we do get a value of 22.5. So using this, we can then go back to this other equation that we started out with, this EIJ, and use it to determine this sigma kk, because we, in the first step, we had these kind of planar values and we wanted to find this perpendicular sigma. Well, in this we have these kind of planar values, we want to find this perpendicular stress, this perpendicular sigma. So, plugging in the values again, we have epsilon ij equal to 1 plus the Poisson's ratio over E times sigma ij, minus the Poisson's ratio over E times the sigma kk, which is the value we're trying to solve for, times this delta ig. So, rearranging the values, we isolate the sigma kk, and then plugging in the values, we get a value of 9.091 megapascals. So, a pretty reasonable value based upon the type of stuff that we've been seeing. So, I mean, what we really found was the properties of the material, that's Poisson's ratio, its shear modulus, and also the stresses that are acting normally to it. So from this equation, we were able to find quite a lot from it. Let's look at a slightly different example, something that doesn't use this type of vector sigma ij notation, but something that maybe deals more with matrices, so a wide range of stuff. So let's try to determine the maximum shear stress that is given by this property. So we have the Young's modulus is defined as 45 megapascals and a Poisson's ratio of 0.21. Okay, so these are, of course, then the inherent materials in the inherent properties in the material. Now we're given an epsilon field, or an epsilon matrix, which shows the epsilon, or the strain, along the x direction, along the y direction, the z direction, and then also the shear strains, so the xy direction, the xz, the yz. We're given all these values, and they are as follows: 1, -1, 4, -1, 3, 2, -2, 4, -2, and 5, all times 10 to the negative fourth. So keeping along with strain being rather small values, this is what we've been given, and we know that the maximum shear stress, this tau maximum, is going to be equal to the maximum sigma value minus the minimum stress value divided by 2. These are principal stresses that we will try to determine, and thus we can determine the maximum shear stress. So we need to find these stresses by using this strain and these two properties we know here, and try to determine this tau maximum. So therefore we need to find these values. So relating, obviously, going back to the equations that we established before, we can relate stresses with the strains, which is what we'll be doing by using this same equation that we've been using in the previous sections. We can determine these stresses, these sigma x, sigma y, and so forth, by taking that same equation and plugging it into a matrix. So we rearrange these strains into a vector, or a single columned array, and we need to relate them into the equation that we had previously. So how do we do that? Well, we relate them via this matrix here. So if we go back, we have 1 minus v times this sigma x times, of course, all of this is equal to this sigma x times this epsilon x. Plus the v's that we found before, and now this is just going back in to these equations that we established before. So these are the same kind of form where we have the sigma over e and the v's. This follows that same kind of pattern where we have this Young's modulus over 1 plus the Poisson's ratio times 1 minus 2 times the Poisson's ratio. That is common for all these values, which is why it's been factored outside. But we have these values here relating these three stresses to these three strains rather to these three stresses. And a similar thing again to these shear stresses relating to these shear strains. It follows that same pattern that we established in the previous section. We've just separated it now into matrices. So it's much easier to work with. It's much easier to calculate all these values by just following these matrices, because they allow us to do all this multiplication in one step. So plugging in for the known values, we know the Young's modulus is 45 megapascals. We know the Poisson's ratio is 0.21, so that's 1.21, and 0.8 in the denominator. And we're able to plug in for all these 1 minus v values, and 1 minus 2v values over 2. We're able to plug in for that, as well as the stresses, and simply multiplying all across, we are able to determine that the stresses caused by these, or the stresses causing these strains, are as follows, where sigma x is equal to 15.84, sigma y is equal to 23.3, and sigma z is equal to 30.7 times 10 to the third. So these are or times 10 to the 6th rather, these are in megapascals. So times 10 to the 6th. So as it follows, as we established in the opening line of this problem, we know that the tau maximum is given by the largest difference in these principal stresses over 2. In this case, it turns out to be 30.71 minus 15.84, so this stress in the z direction subtracted from the stress in the x direction, and taking an average of that, we get 7.435. So this has just been a basic overview on how to do these stress-strain relations for things in 3D. I hope that it's been helpful and that it has cleared up some of the problems you may have with it, but it's simple because it just relates what was done in 2D on a bigger scale with incorporating shears and how that actually affects these stresses and these strains. And by incorporating this, it makes these problem solvings much easier as long as these equations here are pretty well ingrained in your mind. You will have no problem tackling any kind of these problems. They all follow the same basic setup like this. So I hope it's been helpful, and best of luck. Thank you.